As x approaches 3 from the left side, so this negative sign here means from the left side. So it's 3. So x approaches 3 from the left side. Then the y value is approaching 5. So this limit is 5. As x approaches 3 from the right side, this positive sign means from right side. So here's 3, approaches 3 from the right side. Then the function, the y value, is approaching 2. So this limit equals 2. So then as function approaches from 3, which means both from the left and right. So from the left and right, but they're approaching 2 different values. Therefore, this limit does not exist. Limit does not exist. Now D is asking us to evaluate f of 3. So when x is 3, what is the function value? Both are open circle, so that means it's not defined. So we can either write does not exist or undefined. Limit as x approaches 6 from the left side. So here's 6 from the left side is approaching 3. Y is approaching 3. As x approaches 6 from the left side, right, so we plug number closer and closer to 6, and the y value is approaching 3. Equals 3. Now 6 from the right side, positive sign means from the right side, here's 6. From the right side, it approaches 6. As x approaches 6 from the right side, the y value is approaching 3. 3. Limit as x approaches 6. Because left limit and the right limit are approaching same number, this limit exists, and that limit is 3. Because both left and right limits are approaching 3. F of 6, evaluate. When x is 6, what is the y value? Is this open circle right here, which is 1. Evaluate limit when as x approaches 3 of the function x squared minus 9 over x minus 3. So here, if we try to plug the 3 in, we get, let me write on the side here, we get 9 minus 9 over 3 minus 3, which is 0 over 0. So it's undefined. So denominator is 0 and numerator is also 0. So in that case, what we have to do is we need to try to factor or multiply conjugate. But in this case, we can actually factor. So we can write this equals limit as x approaches 3. We always have to keep this limit sign until we evaluate the limit. So we can factor the numerator to x minus 3 times x plus 3 over x minus 3. Now if you look at here, we can cancel this part just for evaluating limit. So then I have equal limit x approaches 3, x plus 3. Okay, let me note here, these two functions are different, but the limit as x approaches 3 are equal. So let me write the next line. We're finding limit as x approaches 3 of this x plus 3. Now we can think as plug number here. Essentially it's approaching, so we can plug 2.9, 2.999. But eventually, well, not eventually, it's forever approaching x approaching 3. Therefore, 3 plus 3 gives us 6. So this limit right here equals 6. Evaluate the limit as x approaches 7 from the left side of function x over 7 minus x. So here, if we try to plug 7 in, we get 7 over 0, right? 7 minus 7, which is undefined in the denominator. But numerator is not 0. So in that case, we're not trying to do factoring or multiply conjugate. We have to do just some more analysis. So the way we look at this, let me write it here. 7 from the left side, negative sign is from the left side, x over 7 minus x. So in this case, we look at numerator and denominator separately first. Where is the numerator approach to? Well, it says it approaches 7 from the left side. So the numerator x is just approaches 7. Then now let's look at denominator, 7 minus x. So here I'm going to draw a number line. Let me draw it right here. And it's approaching 7 from the left side. That means from this side only, right? So approaches from the left side. So that means it's like 6.5, 6.6, 6.9, 6.999, 6.999. All the numbers very close to 7. But since from the left side of 7 is all less than 7. Right? So x is approaching 7, but from the left side, which means that 7 minus this x will always give us a very small number. So as a demonstration, let me do some few calculations. So we can think as 7 minus 6.999, which gives us 0.001. 7 minus 6.9999, even closer to 7 from the left side. So we can think about doing this forever. And we don't need to do it forever, but we can notice the trend. As these values get close to 7 from the left side, we're approaching smaller and smaller positive number. So we can conclude that this expression, 7 minus x itself, is approaching very small positive number. Positive number. But it's very small, it's infinitely small. Follow this trend. Therefore, what's happening in this limit is that numerator is approaching 7. Denominator is approaching very small number. Let me just write small. But note that is really small number. Positive small number. But then 7 is infinitely bigger than this small number. Again, this small number is so small that essentially it can go into 7 infinite number of times. So it's approaching infinity. So this limit right here equals infinity. It approaches infinity. So for these cases, when we have non-zero numerator but 0 on the denominator, which is undefined when we plug it in, then we have to do this more analysis to figure out what the limit is. Evaluate the limit as x approaches 9 of function x minus 9 over square root of x minus 3. So if you directly plug the number in, we get 9 minus 9, 9 minus 9, which is 0, over 3 minus 3, which is also 0. So we have a 0 in the numerator, we have a 0 in the denominator. In that case, we can either factor out or multiply conjugate to simplify the limit expression. So in this case, we can actually multiply conjugate. So I'm going to multiply square root of x plus 3 over square root of x plus 3. So this is essentially multiplying 1. So we're not changing the quantity of the function. We can keep the limit sign until we evaluate the limit. Don't drop this. It's important to keep it until we actually evaluate the limit. So the numerator, we actually don't need to multiply out. Just leave it with the parenthesis multiplication. And denominator, actually, we do have to multiply out. So this, we get x minus 9. So here we see that these two can cancel out for evaluating limit. which is limit as x approaches 9, square root of x plus 3. Then we can try to plug it in. Then we get square root of 9 plus 3, which is 6. So this limit is 6. Okay, let me highlight here. Keep writing the limit sign until we evaluate the limit. So from here to here is when we actually evaluate the limit. So that's why we don't see the limit sign here. Evaluate the limit as theta approaches 0 of sine 5 theta over theta. So here, if we directly plug the 0 in, we get sine 5 times 0, which is sine 0. And sine 0 is 0. And theta is 0, so the denominator is also 0. So we have a 0 over 0 form. So in this case, for trig functions, we have to remember the special limit. Let me write it here. Sine as limit approaches theta approaches 0. Sine theta over theta is always 1. So important part of this limit is that this argument for sine, which is input of sine function, and the denominator must be same for this to work. So here, our issue is that we have a 5 theta here. And there's no way we can get rid of this 5. We cannot divide the input. But we could multiply 5 in the denominator to match this input and the denominator. But when we multiply the 5 in the bottom, we also have to multiply top so that they will not change the quantity. So we have sine of 5 theta over theta. What we do is multiply 5 over 5. Then we can rearrange this. Then we get sine 5 theta over 5 theta times 5. But now we have 5 theta inside of sine and 5 theta in the denominator. So this portion of the limit is 1. And this limit is just 5. So our final answer is 1 times 5, which gives us 5. So here we have to remember that sine theta over theta as theta approaches 0, this limit is 1. Evaluate the limit as theta approaches 0, tangent 4 theta over 5 theta. Here, if we plug the 0 directly, we get tangent 0 over 0. And tangent 0 is 0. So we have 0 over 0. So we do have to do some simplification or rearrangement first. So tangent 4 theta, I'm going to write it as sine 4 theta over cosine 4 theta times 5 theta, which was in the denominator. Now here we have to remember this special limit. Let me write it here as limit of theta goes to 0, sine theta over theta equals 1. So we have to use this one. But when we use this one, we have to pay attention to this argument. This argument for sine must be also the same as denominator. So since we have a 4 theta here, we should have 4 theta in the denominator to use this. So what we can do here is first, let's multiply 4 theta over 4 theta. And then I'm going to rearrange. So the way we arrange is as limit theta approaches 0, I have sine 4 theta. And in multiplication, order doesn't matter here, right? Order doesn't matter. So I'm going to write this 4 theta right here. So 4 theta times 1 over cosine 4 theta. And what we've left is 4 theta from numerator and denominator times 4 theta over 5 theta. And we can also put all this in one fraction as well. Now we see that these thetas cancel out. So what we have is this, or actually we can separate this into three limits. Sine 4 theta. This is just one of the limit law where we can multiply three different limits. 1 over cosine 4 theta times limit theta goes to 0, which is 4 over 5. So we can evaluate one of them one at a time. This one is 1 from here. So now we're evaluating limit, so we should not write the limit sign. Just write the evaluation of the limit, which is 1 times here. We plug 0 for cosine, for theta. So we have 1 over cosine. We have 1 over cosine of 0 because 4 times 0 is 0. And cosine 0 is 1. Therefore, we have 1. This limit is also 1 because cosine 0 is 1 times limit of constant, which is constant. So our final answer is 4 over 5. So let me emphasize here that we need to keep the limit sign until we evaluate the limit. And it's important to be able to show this work. It's not just about the correct answer. Evaluate the limit as x approaches 3, x over 3 minus x. Here, if we directly plug 3 in, we get 3 over 0, which is undefined. We cannot have 0 in the denominator. But numerator is not 0, so that means we have to do more analysis. But this one is approaching 3, which means approach from the left side and the right side. So here we have to actually divide in two cases, where x approaches 3 from the left side and where it approaches from the right side. So we can find each of this limit, and if they have same number, if they approaches the same value, then that is the limit. If they don't approach the same value, then limit does not exist. So let's see. So from the left side, for these, we have to look at separately. This right here approaches 3 because it approaches 3 from the left side. Again, it's not about arriving at there. Limit is about approaching. It doesn't arrive at 3. It just goes towards 3 forever. Here, let's draw a number line. 3 from the left side. That means from here. Left side. Then 3 minus number less than 3, such as 2, 2.5, 2.9999, 2.999. So we do 3 minus number slightly less than 3, which means gives us very small positive number. Small, positive, small number. Let me actually spell out the word. Positive, small number. Very small positive number. Okay. So this entire thing is approaching, let me write it here. As limit goes to 3 from the left side, x over 3 minus x, is approaching infinity, positive infinity. Positive infinity because 3 is infinitely bigger than this very small number. So it approaches, positive infinity. So that's from the left side. Now let's check the right side, from the right side. From the right side, this one also approaches 3. Now this one, the other hand, 3 from the right side, like this. So in this case, it's approaching 3 from the right side. Therefore, we plug number slightly greater than 3. So maybe like 3.11 or 3.01, 3.001. So we do 3 minus number slightly greater than 3. So that means this is approaching very small negative number or negative small number. Because we do 3 minus number slightly greater than 3. So it's like 0, it would be like negative 0.0000001. So very small number. Therefore, this limit right here from the right side as x over 3 minus x, it approaches negative infinity. Because this is 3, approaches negative infinity. Sorry, negative small number. And negative, the small number, can go into 3 infinite number of times, but because it's negative, we keep the negative sign. So you can think as 3 over negative small number, which approaches negative infinity. So now if we look at here, limit from the left side was infinity, limit from the right side was negative infinity. They do not approach the same number or same infinity. Therefore, this limit does not exist. Because they're different. The limit as x approaches 3, which means from the both side, does not exist. That's the conclusion. Evaluate the limit as x approaches infinity of function 11 over x plus 2. So infinity is not a number, so we don't think as plugging in, but we have to think in terms of trend. So as x approaches infinity, that means we plug bigger and bigger number to this function right here. But then what happens to this 11 over x plus 2 as this gets really large, like really, very big, million, billion, trillion, gets bigger and bigger. So what's happening here is that we get actually 11 over infinity. Infinity plus 2 plus the adding 2 is so minimal essentially later on because we're adding such a big number. So this entire thing is approaching 11 over infinity. But then 11 or whatever number is the numerator, this constant number in the numerator is small, infinitely small compared to this infinite. So that means that it is so small that infinity can go into 11 essentially 0 times. So this entire thing is approaching actually 0. So this limit right here is 0. So that's the answer. So we do have to really have to think about this number sense right here. Essentially, any number over infinity is approaching 0. Is approaching 0 because this gets bigger and bigger, so big that 11 will look so small. So small that it's approaching 0. 11 divided by this huge number is approaching 0. Evaluate the limit as x approaches infinity, negative 3x squared plus 2 over square root of x to the fourth plus 10. So when we are finding a limit as x approaches infinity, but we have a rational function like this, or a rational function as in fraction form, what we have to do is we have to divide by the highest degree term for all the terms in the function. So infinity, what we think about is which is the highest term. We have x to the second power. This x to the fourth is essentially x to the second in terms of highest power. Although we can't simplify this to x squared, the is equivalent to the x second power. So what we do is we divide by x to the fourth, x to the second order terms like this. But inside of square root, here we divide by x to the second, right? Because we're outside of square root. Inside of square root, x to the second power is equivalent to x to the fourth, right? So to divide by x to the fourth in the inside of the square root, like this. So then we can simplify. We get negative 3 plus 2 over x squared over square root of 1 plus 10 over x to the fourth. Now here, we're now evaluating 4 different limits. And each of them is x approaches infinity. But this one is just approaches negative 3 is constant. This approaches 1, but we can actually think as square root of 1, which is also 1. Approaches 1. Now this one approaches 0. We have 2 over as the bottom approaches infinity. Bottom is so large that 2 over this huge number is approaching 0. And similarly here as well, approaching 0. And square of 0 is 0. So what we have left here as our final answer is that numerator is just approaching negative 3, where denominator is approaching square root of 1, which is just 1. So this limit is just negative 3. So one thing we have to be careful about this one is when we divide by the highest term, we need to be able to see that this is equivalent to x to the second power in terms of just a term. Because square root of x to the fourth is x to the second power. The graph of the function f is shown below. Identify all the x values where the function is discontinuous, and then identify the type of discontinuity at each point. So discontinuity or continuous at a point means the limit exists, and limit and a function definition at the point are same. But identify discontinuity is just look at the graph and where they're not continuous. So we have one here, and one here. So when x equals negative 4, is not continuous. When x equals 1, it's not continuous. And also when x equals 6, it's not continuous. But all these 3 points have different type of discontinuity. So for negative 4, the limit from the left exists, and limit from right also exists. But the limit from left and right are not equal to each other, which means the limit as x approaches negative 4 does not exist. In that case, we have a jump discontinuity. Visually, we can tell that there's a jump. Here's a little jump, right? Maybe draw this way. Here's a little jump right here between left and right limit. That's how we can visually tell. But if no visual is given, we can tell that here, the left limit, negative 4, as x approaches negative 4 from the left side, is different from as limit as x approaches from negative 4 to right side. So when left limit and right limit are not equal to each other, but they each itself exist as a number, because this limit right here is what? From the left side is approaching 2, right side is approaching 3. They're different number. And then we have a jump discontinuity. Jump, let's just write jump. Jump discontinuity. And negative 4. And 1, in the other hand, limit from the left side and limit from the right side are same. They approach the same value. But the function value is different. So for x equals 1, limit as x approaches 1 exists. And in fact, there's actually 3. But the function value at x equals 1, or let me write it x equals 1. When we evaluated 1, it is 1, because it's defined at 1 right here. So when the limit value and the function at that point are not equal to each other, we have a removable discontinuity. Removable discontinuity. It's called removable because we can remove the discontinuity by just filling one point. That's the one good way to remember. We can remove the discontinuity by just filling this one hole. But when graph is not given, we know we have removable by comparing the limit and function defined at this approaching value, f of 1 in this case. And when they're different, then we have removable discontinuity. Now, when x equals 6, as you can see, limit from the left side is approaching infinity. Limit from right side is also approaching infinity. So in that case, we have infinity. Infinity type of discontinuity. I forgot to box this right here. So here we can just tell by limit from the one side. Even if one side goes infinity, other side doesn't go infinity, we still have infinite type of discontinuity. So limit from 6 to the left side is positive infinity. So that alone tells us that we must have a discontinuity at 6. And that the type is called infinity because one of the limit goes to infinity. In this case, both from the left and right side happens to go infinity. But in order to be infinite type of discontinuity, only one side needs to go infinity.